So no, this is fine. But yeah. Okay, so today we're going to be talking about mean value theorem. So you guys can turn to page 6.
Sophia's coming too.
Okay, thanks. Yeah. Okay, so this is a an important theorem, extreme value theorem, and today mean value theorem. These are the two most common theorems that gets applied on AP exams from first semester topics. Okay, so you're almost guaranteed to see some variation of this show up on the free response on the AP exam. So we use mean value theorem to justify conclusions about a function over an interval. So it says this, if a function is continuous over the interval, okay, so you see that continuity condition show up again and again every time we introduce a theorem. So let's say our function is continuous over the interval from A to B. Those are our endpoints. So the function needs to be connected, cannot have any holes, cannot have any asymptotes. And second, it needs to be differentiable as well. Does anybody know what does this mean?
Max and minimum.
Differentiable means you're able to find the derivative at every point. That means a smooth curve. Okay? That means there are no sharp turns. It can be a smooth curve all the way through. Every point, there is a slope value that exists. But we only need the function to be differentiable over the open interval. So that means in order for us to prove this theorem or to apply this theorem, the graph does not have to have smooth points at the endpoints. As long as it's smooth between the endpoints, that's sufficient. Okay,
Well,
so
why is one in bracket and one in like this?
So we need continuity. We can't have any breaks even at the endpoints. So that's why we have to include the endpoints. But it does not have to be smooth at the endpoints. So that's why the restriction is not as heavy for the differentiable portion. So now what can we guarantee? Once we have these conditions established, there exists a point within the open interval where the instantaneous rate of change equals the average rate of change over the interval. So within these two parts, there is an algebra portion and there's a calculus portion, and we're connecting those two together. So let me show you what this means here. Average rate of change equaling the instantaneous rate of change. Let's say we had points A and B on the graph. Let me see if I can sketch my graph here. Okay. So let's say there's point A here and point B here. Okay. And there's a smooth curve that lives, I'm sorry, I'm a little bit off here. Okay. And the average rate of change is the slope between these endpoints. Okay, so it's just change in y over change in x. So let's say that average rate of change is something like a 2 or a 1/2 or 3, right? Some positive slope. So if there's a slope of, let's say 3 here, example, then can I guarantee that there must be some slope that's also exactly 3 along this interval? Yes, okay, so that's what mean value theorem is guaranteeing, is that if my average rate of change is a certain value, then there's going to be an instantaneous rate of change. There's going to be an exact slope somewhere along the graph that is going to match that average rate of change exactly.
Like 2 different lines.
Hmm?
So like one line's like this rate of change and just another line will be exactly the same. Like
Right, right. So let's say this is a slope of 3, then we must experience an exact slope of 3 somewhere along that interval. Okay. Somewhere along that graph. So here's the formula. We know that if I want to find instantaneous rate of change, it involves the derivative. And then the average rate of change, however, is just algebra. It's just slope formula. So f prime of c is equal to f of b minus f of a over b minus a. Okay, so I think I want to just share with you a analogy that hopefully you'll find more intuitive, because this does feel a little bit like, you know, what does it really mean? So let's say you're on a you're on a road trip, and you calculated that you traveled 300 miles over a 5-hour period. Okay, and let's say you're just driving on the highway continuously for that long, but it took you 5 hours to make that trip. Now, what is your average speed? 60 miles per hour, right? Now, assuming that you're not on cruise control, can you guarantee that you're always traveling at this speed the entire way? Okay, no. But so that's basically this is the average. So this is your average speed. But is it possible to travel your entire trip, average this mile per hour, and never reach this at any moment in time? That's not possible, right? So you know that some point along along your journey, you're going to reach exactly 60 miles per hour. Maybe just once, maybe more than once, but at least once, right? So that's what that's an example of mean value theorem, is that, you know, if my average rate of change is 3, there must be, or sorry, if my average rate of change is 60, then there must be a time when the exact speed or average, that exact rate of change is also 60 miles per hour. So what we would be doing here with mean value theorem, we would be trying to find exactly at what moment in time did you reach that average rate of change. When did you reach that 60 miles per hour? Okay, so that's what mean value theorem would be trying to find. All right, so let's talk about how we can apply it. It says use the function. Yeah.
So couldn't it reach 60 miles per hour at like 2 different points still?
Yes, it could.
Okay.
But you're right. We could draw the graph where it's to their point, but all mean value theorem cares about is that we can guarantee at least once. Now, if there's more than one, then we would find more than one. But there's no way that we can go through this process and not have at least one. Yeah. So basically, to answer your question, one or more. Okay, one or more. Okay. Use the function negative x squared plus 3x plus 10 to answer the following. On the interval 2 to 6, what is the average rate of change? So here, we're breaking up mean value theorem into 2 parts. We're going to do the, I'm going to show you exactly how I want you to do this. You're always going to find the average rate of change first, and then you'll do the instantaneous rate of change second. Okay, and there's a reason that we want to do it this way. Otherwise, it's easy to make a mistake or go down the wrong path. So before we find the average rate of change, I just want to kind of go through the process for mean value theorem. We have to always make sure we talk about our conditions. Okay. Now, is this a smooth curve here? Negative x squared plus 3x plus 10.
Yeah.
Okay. It's a polynomial, no holes, no asymptotes, no breaks, no sharp turns. it'll fulfill both conditions, but we just have to make sure that we write them out in this way. You're going to say the function f of x is continuous on this closed interval from 2 to 6. And you know the function is differentiable on the open interval 2 to 6. Okay. So I'm going to do this every time so we can kind of just get into a habit of establishing our conditions. Continuity is with bracket, differentiable is with parentheses. Now it's continuous differentiable everywhere, but we just are we're just focused on our boundaries and our bounds, and that's why we have to include 2, 6 both times.
I didn't know it's continuous.
Because this is a polynomial here, so polynomial is just going to be a nice in fact, this is just going to be a parabola, right? So parabola is going to be a nice smooth curve, unless it's something strange like absolute value function or a cube root function or a rational function. Then we have to worry about, okay, is there continuity or differentiable issues?
Like for you to be able to like continue, it has to be both continuous and.
That's right. For mean value theorem, it must be both continuous and differentiable. However, remember yesterday, extreme value theorem, it only requires what?
Continuous.
Yeah, it just requires continuity, because extreme value theorem doesn't need it to be a smooth curve. It can have a sharp turn because we're looking for a max and min. We're not trying to guarantee anything that's slope related. Okay, so first things first, find the average rate of change. So we're just going to find the slope between the endpoints. So what information do we need if I want to find the slope between the endpoints? And again, these are both x values. I need to plug in and find the what? Find the y values, right? I need order pairs before I can find slope. I have x values, but I don't have full order pairs yet. So we'll do f of 2. So -4 plus 6. 2 plus 10 is 12. So I have 48 minus 36. Wait, -36. Sorry, -36 plus 18 plus, yeah, I had -8. Let's see. Yeah, so 28 minus 36, -8. So let's find the slope between the endpoints. So changing y over changing x. So that's the average rate of change between the two endpoints. It's the slope of -5. So maybe a graph that looks like this here. Between two endpoints, the slope is -5. So we know that somewhere along the curve must also experience a slope of -5 somewhere along that path. And that's what mean value theorem is doing, is trying to find that location for us. So on the interval from 2 to 6, when does the instantaneous rate of change equal the average rate of change? Now we can move on and find the what? Derivative. Okay. So let's find f prime.
What's your answer for a? Like,
oh yeah, it's -5.
M equals negative.
Mm-hmm. So I just drew a example of that, of what that could look like. A slope of -5 could look like that between the endpoints. Okay, so what's f prime? Okay. So I'm going to ask the derivative to tell me where along the curve are you going to experience a slope of -5. So we're going to insert the -5 into the f prime slot. Does that make sense? That the -5 doesn't go for the x, it goes in for the f prime, because -5 is the slope, not the location. So we're kind of working backwards a little bit here. We're setting f prime equal to the average rate of change. Now I'm going to solve for x, and when I solve for x, I can find the physical location on the curve where that exact steepness is going to occur. Okay, so I'm going to just move things around here. I'll say this 2x equals 5 plus 3. I'm just swapping the negative 2x and negative 5 around so I can just have positive values to deal with. Okay, so 2x equals 8. X equals what? 4. And we call this x the c value since that is the notation that is used for indicating the location found by mean value theorem. Yes, so it says when does instantaneous rate of change at x equals 4, or we can say at c equals 4. So maybe if a graph looked like this. This is a value of 4, and along that path, there's a slope of -5 there. So we're basically asking the curve to tell us where is the graph going to experience that slope of -5, and it's at x equals 4.
We did say like instantaneous rates at c equals 4, or you can say c equals 4.
It's at c equals 4. Or we can say at c equals 4, the instantaneous rate of change equals the average rate of change. But you don't have to write all that out. You just have to understand that.
Why do you say f prime x equal to like the slope?
Because we know what slope we want, right? We're going to ask the derivative to find the location where this slope exists. So the -5 in for the x wouldn't make sense, right? Because -5 is not a location; it's a slope value. So slope needs to go in where the slope value lives, or where the slope variable is. Okay, the issue that students have with mean value theorem, well, first, it's a relatively involved process because you have to spend all the time to find your slope between the endpoints, and you got to find the derivative, and then you got to set them equal to each other, and then you got to solve for x. Okay. But I really want to emphasize that go ahead and find your average rate of change first, right? Your tendency, I'm going to let you know that your tendency is you want to find the derivative first. Because it just feels like, okay, f is f prime. That just feels like an easier thing to do than plugging stuff in. But don't do that first. Okay, find your y value, get all your algebra portion out of the way, get that slope value, and then find f prime, and then you can set them equal to each other. The reason why I don't want you to find the derivative first is if you find f prime first, what's going to happen is you're going to be tempted to want to insert the 2 and 6 into f prime, and then you're going down the wrong path. Then you're trying to do f prime of 2 and f prime of 6, and then you're trying to do the slope between these slope values, and that's, we don't want to do that. So if you can remind yourself to take care of your algebra portion first, then when you find the derivative, you know that you're going to involve this number somehow, so then you're going to start working with this rather than try to involve the 2 and 6 into f prime. So we don't want to insert 2 and 6 into f prime. We want to insert 2 and 6 into the original function because you want to find the slope between the endpoints. Okay. Just distinction between mean value theorem and intermediate value theorem, because they kind of can feel the same, especially in a word problem or in a AP Calc response question. So mean value theorem is trying to guarantee whatever the slope between the endpoints, you can guarantee that there's going to be another place where that slope is going to also occur. But intermediate value theorem says that it's just trying to guarantee a location. So if I have on a given interval, you will have a y value at each of the endpoints of the interval. Every y value exists between these two y values at least once in the interval. So MVT says if I have a low y value of -10 and a high y value of 6, then every intermediate value between those two y values will be reached at least once somewhere along that curve.
Looking for the values of the rate change.
Right, it's looking for the value instead of the rate change. Yeah,
Did we do MVT before? Like,
we did, yeah. So that was off the first unit when we did part of our limits unit. Okay, so I want to come back to some of the I want to come back to some of I'm jumping around here. This is off the BC packet here. So if you guys can turn to page 8, and let's do a full practice problem of mean value theorem, so you kind of just get that some of that steps under your belt a little bit. So let's try number 4 on the bottom of page 8.
Theorem is like the
Sorry.
like Rolle's theory.
Yeah, Rolle's theorem. We're gonna do that later. But the bottom of the page here is still mean value theorem. Number 4 says use mean value theorem to find instantaneous rate of change that's equivalent to the average rate of change. So let's focus on the average rate of change first. But what are our first 2 conditions that we have to make sure we establish? Continuous differentiable. Is this continuous differentiable?
Yeah.
Yes, polynomial, right? You have a there's nothing strange about this function here. Continuity is with brackets, differentiability is with parentheses. Okay. Mean value theorem is exactly that. Instantaneous rate of change, set it equal to the average rate of change. But which one do I want you to do first? The average rate of change, which means the non-calculus portion. Okay, don't take the derivative yet, because that's going to potentially make you go down the wrong path. So what should we do then? Plug the x values in. Okay, plug the x values in. So imagine how you would approach this problem if you were trying to find, just want to find slope between the endpoints.
So the opposite. Oh, okay. Never mind.
So I had,
That's the same thing as flat three.
yeah, that's right. F of x, same thing as y. Four plus 10 plus 2. I'll do this. Average rate of change is equal to, so change in y over the change in x. We'll set this value to the side because we know that's our goal. We're trying to figure out somewhere along the curve must experience a slope of -11. We're going to be using the derivative to help us with that. So now we can do what?
Derivative.
Yeah, now we can focus on the instantaneous portion, right? So y prime equals this derivative.
2x minus 5.
All right, we got to involve the 2x minus 5 and negative 11 somehow. So what do we do?
Put the 11 in x. We're putting 11 to the y.
Yeah, so negative 11 is in for the slope, right? So here's your average rate of change. Here's your instantaneous rate of change. We're going to set them equal to each other.
Average rate of change equals m, right?
That's right, it's m. Yeah, you can say average rate of change, you can say m. Yeah. So this tells us that along this curve, this graph is going to experience a slope of negative 11 when x is negative 3. And that is guaranteed to live between the endpoints, right? We know somewhere between negative 4 and negative 2, the graph has to reach a slope of negative 11, and we found it here. Okay, I want to talk about something that's related to mean value theorem, which is a very specific version of mean value theorem called Rolle's theorem. Okay, I'll give you guys another moment, and then we'll go to the top of page 8. All right, so Rolle's theorem says this. We're still going through the same process as mean value theorem. We still want to make sure a function is continuous on the with brackets, differentiable on the open. But there's a third condition, because Rolle's theorem is not just trying to ask for any slope, it's trying to ask you, is there a slope of 0 somewhere along the curve? But if I want to guarantee a slope of 0, that means my average rate of change also has to be a slope 0. But if my average rate of change is a slope 0, what does that mean? That means a horizontal line means that both my y values on my points have to be what?
Same.
The same, right? So that I can do change in y over change in x will give me slope 0. So if this is a y value 3 and that's a y value 3, then I know that my slope is 0. If my slope is 0, then I can guarantee somewhere along the curve there's also a slope 0. So mean value theorem is just trying to guarantee you whatever the slope is between the endpoints. But Rolle's theorem is saying, yes, but I need that average rate of change to be a slope 0. Okay, so that I can guarantee a slope between the endpoints, a slope on the curve being exactly 0 as well. Okay, so let's try example 2 here. So Rolle's theorem, let me write this here. It's still the same process. We still are trying to match the instantaneous rate of change to be the same as the average rate of change. It's just that we need this to be a 0 slope. So that's the only condition, is that it's a very specific version of mean value theorem. Okay, determined Rolle theorems can be applied. So again, x squared minus 3x plus 2. Any issues here? Will this pass both our conditions? Yes, so let's go ahead and write those out. You're going to write out the condition the same way, because really Rolle's theorem is just, it is mean value theorem. Okay, so I don't want us to think of it as completely separate. It's just a very specific version of it. So just like before, we're going to focus our attention on the average rate of change first, right? No derivative, okay? Force yourself to get all your algebra information out. So we're going to plug in the endpoints, just like how we do with mean value theorem. You don't want to find f prime. If you find f prime, you're going to be tempted to want to do f prime of 1 and f prime of 2, which is not the right process. All right, f of 1, I plug 1 in for x, I get, which is 0. Okay, plug 2 in. Also 0. Okay, so what's the slope between these two endpoints? 0. So my average rate of change is 0. Can I guarantee a slope of 0 somewhere along the curve? Yes. So now we're going to look for that location. Okay, so now we can find what? Derivative f prime. Okay. X squared minus 3x plus 2 becomes what? All right, what's your next step? Good. So it's basically, I have my derivative function. I'm going to ask my derivative, okay, I want a slope 0. Can you tell me the location where slope 0 occurs?
What's your reference point?
That's right. And the location that I get has to be between 1 and 2 because those are my boundaries, right?
B3/2.
Mhm.
3x.
Which does fall between 1 and 2 because 3/2 is 1.5. So if we were to sketch out the graph is going to have a slope 0 at exactly 1.5 along this parabola. Maybe something like that.
Is there gonna be times where they like draw it out?
No, I just want to just give you a visual so that you know what we're trying to achieve here.
So what's between this theorem and the other one? Significant difference.
Oh, mean value theorem?
Yeah.
Okay. So mean value theorem can be any slope that we find. It could be a slope 2, it could be slope 4, it could be slope 8, it could be slope -16. But Rolle's theorem has to be slope 0. It's just looking for slope. Yeah. It's not a critical. Oh, yes, it is also a critical point where if I were to set exactly, you're right. Yeah, it is a critical point. Right. But the reason why this is different is because now I'm trying to, can I guarantee that my critical point is going to live in this interval? So that's what Rolle's theorem is saying. Okay, even if there's a slope 0, if it's not inside the interval, then Rolle's theorem would not apply. Yeah, but you're right. It basically is finding a critical point. But Rolle's theorem is saying, can I guarantee a critical point of slope 0 exactly between these two intervals? In order to guarantee that, my two endpoints need to show the same slope.
Are you able to do one a trick yet?
Not yet, no. We're gonna skip that one. Not necessarily. Right, but yesterday was extreme value theorem. So extreme value theorem is using critical points as a candidate for a max or min. But Rolle's theorem is just asking, can you guarantee a slope 0 with just these information that's given? So that's the difference. The Rolle's theorem is just, can I guarantee a slope of 0? Extreme value theorem is using slope 0 as a candidate for finding a max or min. It could be, yeah, it could be a max or min, but that would be the process for extreme value theorem. Yeah, but here, the scope is smaller here. It's just, I'm just looking for slope 0. Can you just tell me there's a slope 0? Extreme value theorem, in a sense, is asking for more. And can I find a max or min? So I need candidates to help me prove that point. Okay, let's try number 6 on page 9. Actually, I'll say that for a little bit. This is a little bit heavy on the algebra here, so. Okay, page 10. Okay, let's try 41. Okay, so our function x to the 2/3, our function is going to be continuous and differentiable. So we'll go ahead and just make that out, write that out. Okay, what's our first step? Yeah, find the y values. Don't do derivative. Okay, find the y values. Once we find the y values, then we do what with this?
We find we find the rate change.
Yeah, rate of change. Good. So slope, right? Let's focus on the average rate of change first. So slope, you can do average ROC, or you can say M, just indicating that you're trying to find the slope between the endpoints. Okay.
Derivatives next.
Now it's derivative. Okay, F prime.
2/3 x Latin derivative.
Let me clean this up. So we know that somewhere between 0 and 1, this curve is going to experience an exact steepness of exactly 1 somewhere along that path. And we're trying to figure out where that's going to occur. Okay, everything that we have is in front of us. What's our next step?
Well, you can say what equal to 1.
Right, good. So 1 goes in for the F prime. 1 is not a location. 1 is the slope. So you're working backwards here. You're giving the derivative the slope, and you're turning around and asking the location where that slope exists. I'm just going to cross multiply here. Okay, what's next?
Divide by 3.
Okay.
Root of some points.
Well, it's already cube root here, so how do we undo cube root?
Cube it.
Cube it, yeah. We always want to double check, is this value between my interval? Yes, it's a fractional value that's more than 0, but less than 1.
You've always been final answer in terms of C2, right?
Yeah, C is a representation of the x value of our answer.
You probably give up like marker point off, but next week.
Probably not. Okay, let's do one last one. Number 35, part B. Use mean value theorem to determine the point C on the interval so that the tangent line is parallel to secant line. So
We can't find the secant line. Secant line equation already found.
think of it this way: tangent line and secant line is basically average rate of change equaling the distance rate of change.
Okay.
So we don't have to worry about the actual line itself, just have to worry about the slope. So go through the same process here. Our function is continuous and differentiable, right? Okay, what's next?
Then you plug in the x values.
Yep, find the order pairs, find the slope, right? And this is not the order pair. Those are both x values. Okay, once you have your order pair, then you find what? Slope. So I know the slope between the endpoints is -1. I'm just looking for along the curve where that slope of -1 is also going to show itself. So now we can find the what? Derivative. F prime equals.
-2x. That's it.
And then final step,
Plug in the -1.
in for
The prime.
F prime, yep. So that means this tells us that at exactly 1/2, the slope of that tangent line is going to match the slope of the secant line. Okay, check your calendar. You guys have homework from 5.2. Get your phones. Yeah, thank you. Okay. All right, mark it down. Thank you.
Wait until tomorrow.
Tomorrow, okay.
On both days, I'm working on it.
Okay. Thank you.
I have a question. So how do you solve like A?
Oh, find the equation of tangent line. So you find the slope to the interval and just do point slope.
Okay.
You can choose either point for slope. Okay, great. I'll mark it down. Thanks.
So you should go to our workshop for today.
Is it today?
Yes, second.
What's that? Wait, it's did already. Today, okay.
He tells us every day. Right? Why?
It's in the auditorium.
Auditorium.
That's right. That was